Howdy, everyone. Happy Friday. I hope you're all doing well. I hope you've had a chance to do the math riddle. If you haven't, I'll give you another 30 seconds to try to finish it. So in 30 seconds, I'll ask everybody to send the answer to everyone on chat, and let's compare answers. Okay, well, most people have signed up, so go ahead and send the answers to chat, and let's look at what everybody's getting. Okay, well, we're getting a few odd ones. The common one, as you'll see, the answer is gray. It's kind of interesting to see how people spell gray. There are two options with an E, or which most people are choosing, or you can write it with an A. But anyway, everybody should have come up with the letter D, and then most people pick Denmark, and then they pick elephant, and then they pick gray. You can pick Dominican Republic and maybe come up with an ostrich. Some people come up with an eagle after Denmark. You can do the Democratic Republic of the Congo. That's still a no. But anyway, gray wins quite a lot. So it's nice to see it from this class. We probably had about 150 people answer. But I think this is kind of a clever thing that people do. Okay, does anybody have any questions about getting the book or the notes or anything else logistically about the course? Let's see if there's more coming in on the chats. We're getting oranges and yellow with spots and so on, but okay. I won't look at any more answers on chat for a while. Okay, so last time I very quickly wanted us to be reminded about classical mechanics. And so we talked about some of the aspects there. And we first looked at some of Newton's laws. So we saw kinetic energy was 1/2 mass times velocity squared. We could also write that as momentum squared over 2 times the mass. We looked at a couple forms of potential energy, one for the harmonic oscillator, which represents springs, or electrostatic attractions or repulsions. And so we can have energy of motion, kinetic energy, or we can have potential energy. We could also have a ball on top of a hill with potential energy, but that won't apply much to what we're going to be doing in this course. Let's go a little bit further with Newton before we get started on quantum mechanics today. So total energy is always kinetic energy plus potential energy. And we will see that's also the case in quantum mechanics. But when we get to quantum mechanics, we won't write 1/2 mv squared for kinetic energy. We'll have a differential equation type of form. The potential energies might be very similar, we'll see. But I want to just go through a little bit of mathematical manipulation and see how we can work with equations of this type. So first, let's do a problem with potential energy 0. So this can be a particle in a vacuum just flying around, no gravity acting on it. And so total energy would be equal to the kinetic energy plus 1/2 mv squared, just our standard equation for kinetic energy. So next, let's write it maybe the way Newton would have. You remember he used calculus. So let's say velocity is dx dt. X is the change in position with respect to time. And so we can rearrange this by solving for v. We have to take square root of both sides and also then wind up dividing through by mass and moving the 1/2 to the other side. So this creates a differential equation. We will look at some differential equations in this course. I typically won't ask you to solve them, but I may often give you solutions and ask you to show me that the solutions actually work. Anyway, this is a pretty straightforward one. Since we have dx is equal to this constant times dt. So we integrate both sides, and this is what we get. So if we want to know the position at time t, it's equal to the position at time 0, or starting point, plus this constant times t. Or we could even write it in terms of momentum if we want to, like this. So this is just another form of writing it. My main purpose of showing this to you is how we can look at the math. And secondly, it just reiterates what we have in classical mechanics. It says if we know the initial position and the momentum, which also means we would know the velocity, then you can calculate the position of the particle at any time. And as I said last time, this is similar to just calculating where your car is going to be if you're starting a drive from College Station to Houston or Dallas or wherever. So this is the classical mechanics view of where things are. It'll be different when we get to quantum mechanics. Okay, let's also look at Newton's second law, just to look at the mathematics of it. We all remember F is equal to ma. Acceleration, you remember, is the rate of change of velocity with respect to time. Velocity is dx dt, so acceleration becomes d squared x dt squared. So this is the mathematical form of the expression. Now to turn it into something else, let's start with the formula for momentum. So momentum is going to be mass times velocity, or mass times dx dt, which is the velocity itself. And if we take the derivative with respect to time of momentum, then it becomes mass times the second derivative with respect to dt squared. So you'll see that's just what we have up here in Newton's equation. So Newton probably wrote this as force is equal to the rate of change with respect to time of the momentum. And again, this is a statement of classical mechanics. If we have a constant force acting on a particle or an automobile or whatever, we can always calculate its momentum, and therefore we can calculate its position as such. Okay, well, next I'm going to go and talk about why we're not happy with classical mechanics. But let me first show you a picture of Isaac Newton. When we talk about quantum mechanics, we're going to say that we have to go beyond Newton to talk about things. But as you are all aware, I'm sure, Newton coming upon the stage in the 1600s really transformed the whole world. All of Europe in particular had gone through the Dark Ages. Everybody thought whatever was happening was an act of God. The ball rolled down the hill. It was because God wanted it to happen that way. And Newton figured out that you could actually write formulas for representing what's going on. In fact, for 1,000 years, things were so backwards that when people wanted to do medicine, they went back to the Greek science from a couple thousand years earlier, or at least 1,000 years earlier when they did that. So Newton really transformed everything when he came along. Now, let me ask everybody a chat question. As you know, Newton used a lot of calculus. Who invented calculus? So I'm curious to see your answers. If you would send me a chat, send everybody a chat. We're getting a lot of Newtons. Oh, we get some correct answers too. We have the Arabs somewhere. I don't know. They may have. Anyway, most people are saying Newton. A few say Newton and Leibniz. Some say Leibniz. So actually, this class is much better read than many that I've seen in the past. So I congratulate you on that. So let me tell you a little story about the invention of calculus. From sources I have read, people believe that it was done independently by Newton and Leibniz. In fact, we know for sure that when you write ddx of something, that comes from Leibniz and not from Newton. In fact, if you look at the stamp honoring Newton at his 350th birthday, it says F delta T and delta MV instead of having the dt or dv or whatever we're going to have in the equation. Anyway, from the story I read, both of these guys developed calculus. And in those days, of course, we didn't have journals and so on. Most of science was done by communication with letter, which may have taken months to go from one place to another. And so it's kind of hard to keep track of whenever anybody invented something. Well, Newton obviously was ultra brilliant, and he came up with all his equations for gravity and kinetic energy and everything else like that. And he got himself elected to be president of the Royal Society, which was the foremost scientific body in the world, located in England in the 1600s. And Newton was furious that everybody wasn't saying he was the fellow who invented calculus. So what he did was he appointed a group of his friends to study the issue, to see who invented calculus. And just to make sure he would get the right answer, he forged a letter as if it had come from Leibniz. And I don't know the exact content, but the gist of it was, "Dear Newton, you're right. You're the only guy that invented calculus. I'm sorry that the world is confused, thinking that I had something to do with it." So those weren't the words, but anyway, Newton stooped pretty low to try to affirm that he was the only guy doing it. Anyway, so great scholars and great scientists aren't always the nicest of people, as we can see. Okay, so that's enough about classical mechanics. So we can now return to seeing why people started not being content with all this wonderful stuff that Newton had come up with. So I want to take a sort of a historical approach and go back, and this goes back now about 140, 150 years, where observations were being made that didn't quite fit what Newton had come up with. Most of you, or at least many of you in high school, probably did the Bunsen burner experiment, where you turned on a Bunsen burner flame, and then you threw some salt into it, something like barium chloride, and you saw green colors. If you threw a potassium salt in there, you'd see pink color, or sodium would be orange, and so on. And basically what was happening when you did that is the flame excited the ions or atoms that were thrown into the flame into some excited states, and then the energy was re-emitted. But it was always re-emitted at the same frequencies, what meant that you were always getting the same color, green from barium, and so on. Bunsen, by the way, was a famous photochemist. He's mostly known for his little Bunsen burner, but he did a lot of studies of that time, doing spectroscopy, trying to see why you get different colors from different things. All right, well, related to this, people became quite scientific about it. And they used prisms in general to see what colors came out from different materials. And one of the materials that was most often studied was hydrogen, and actually the hydrogen atoms and not the hydrogen molecules. So people would find a way to dissociate the H2 molecules, split them into hydrogen atoms, and then they would look at the emission of the light, look at the frequencies that came out. And what was observed is that only very specific frequencies came out. Certain different colors occurred, and they came out at distinct energies. As I'm about to tell you, the relationship between frequency and energy is Planck's relationship here. Delta E is equal to h nu. H is the constant known as Planck's constant, named after the German physicist Max Planck. And we use our symbol nu. This is a Greek letter nu, N-U, for the frequency of light. And so we're going to say light particles are going to be photons, and they're each going to have an energy h nu. And whenever you have an energy difference between two possible energies, you're going to have light emitted at that energy. Now, this kind of diagram you may not have seen before. This is an energy diagram, and we're going to see a lot of this during the semester. The abscissa really doesn't mean anything. It just allows me to draw a nice horizontal line to represent the possible energy. But what I'm showing here are these are possible energies of an atom, such as a hydrogen atom. You might think of this as the 1s orbital, the 2s orbital, the 2p orbital, and then higher orbitals like the 3s and so on. So different orbitals in atoms are going to have distinct energies. And what people discovered in the mid to late 1800s was that you would get discrete emission of light from one of these energy levels to another. And then, as we're going to talk about later, we'll see how that fits into the atomic model of the atom. Okay, so nothing that Newton had done could explain this. So this was a puzzle for many people. So as I just said, each energy change is associated with a specific photon or a light particle. It has energy h nu. And one of the first things we're going to be talking about in this course is atomic structure. And so we'll see why we get these kinds of emissions from atoms. Okay, the next experiment I want to tell you about is the photoelectric effect. And this is actually what Einstein received his Nobel Prize for. Everybody knows about Einstein's special theory of relativity and general theory of relativity, and most of us would have assumed that that's what he got Nobel Prizes for. But in fact, it was explaining the photoelectric effect. And I'm going to jump forward a couple of pages where I have a prettier picture. So here it is, giving an example of what is going on. So all we're doing here is just shining light of a particular wavelength. Early on when this was done, probably people took white light, maybe even sunlight or electric light shown through a prism to generate one frequency of light, and then of course one wavelength of light. And then they wanted to see what would happen. So in general, the photoelectric effect is one where you shine light onto a metal. In this case, we have potassium. And at some point, when the energy gets high enough, you start getting electrons coming off. And the electrons are going to have a certain kinetic energy, just by our standard Newtonian type formula, 1/2 mv squared. Here, m sub e means mass of the electron, v sub e means velocity of the electron. But look at what we have. If you shine light at 700 nanometers, this happens to be red light. And if you apply that equation I gave you relating frequency and energy, you find that this comes out to be 1.77 electron volts. When you do that, you get no electrons coming off. As I'm noted on the bottom, or as the slide shows, potassium requires 2 electron volts to kick off the electrons. All right, well, let's change the frequency of light down to 500. It's not the frequency, but the wavelength down to 550 nanometers, which is higher energy. Frequency and wavelength, as I'm going to remind you, are reciprocally related. And the formula is actually wavelength times frequency is equal to the speed of light. But we'll see that again later. Okay, so we're lower in wavelength, we're higher in energy and higher in frequency. We put in 2.25 electron volts. That's more than enough to kick off electrons, and they come off at this particular velocity from which you can calculate the kinetic energy.
Professor,
a question?
And the electrons are getting, they come from the metal, correct?
The electrons are coming from the metal. So metals are made up of atoms, and so what we're doing is we're kicking electrons off the atoms that are in the metal.
Okay, thank you. That's what I wanted to clarify.
Okay, so notice what happens here. I mean, you can't tell from the numbers, but we put in 2.25 electron volts. 2 electron volts is required to get the ejection of electrons to start. And that remaining difference, 0.25 electron volts, turns into kinetic energy. So you'd find that this amount of velocity with the mass of the electron is exactly 0.25 electron volts of energy. Okay, well, let's go even higher in energy. We're going down in wavelength, 400 nanometers. We're putting in 3.1 electron volts, and you'll see the amount of the velocity of the electrons goes up even more. Okay, so let's go back to where we were. And I have the same picture, but not quite as pretty. But here's a summary again of the observations. No electron is emitted unless the frequency exceeds the threshold value. Frequency is directly proportional to energy, so you have to have enough energy you're putting in. The kinetic energy of the emitted electrons is directly proportional to the frequency of light. So higher frequency gives you higher energy, you get higher kinetic energy. Now notice this is important. The intensity of light cannot be used to turn on or off the electrons. So no matter how many of those 700 nanometer photons I use to hit that potassium, I'm not going to get any electrons. Only when I go to a low enough wavelength, high enough frequency, high enough energy, do you start getting electrons coming off. In case I forget to tell you, let me just point out that this method is used constantly in phototubes. A lot of people do spectroscopic experiments, and they have photomultipliers, phototubes, and basically they take light signal and they convert it into electrons, and then the electronics of your detector can tell how many photons were actually emitted at a particular value. Okay, well, here's our picture. Again, think of this as an atom. We have 2 possible energies. I've labeled one as an initial state and another as a final state. I'm not going to get into this now, but this is very similar to an ionization potential. In freshman chemistry, you learn that you can put in a certain amount of energy to ionize a particular element like chlorine or oxygen or whatever, and that was the ionization potential. So what we need in this experiment is we need that much energy to kick the electron from its lowest state to where it can actually be released from the atom or ion or whatever you're talking about. So the final state represents the case where the electron is free to fly off. So this is the threshold energy. We saw for potassium, this was 2.0 electron volts. And And in terms of frequency, it's going to be Planck's constant times the threshold frequency, so h nu threshold. So if the frequency is too low, the electron can't get up to the final state and be released, and so there are no electrons. When it's high enough, whatever energy is greater than this threshold energy gets converted to kinetic energy. So this is basically what we get out. The kinetic energy, 1/2 mv squared, is equal to the energy in minus that required to remove an electron. Let me mention to you right now, this is a type of problem I love to put on the first hour exam. I might give you the threshold frequency or the actual frequency and ask you to calculate what the kinetic energy of an electron is. But I can give you any two of these pieces of information and ask you to figure out what the third one is. As I said, this is a very important experiment because it's used in photomultipliers and so on. I'm looking at chat.
This is, Professor, I think this is also talking about conservation of energy at the same time.
Yeah, you're right. You're right. When I get to the next example I'm going to talk about, I'll in fact emphasize the conservation of energy that we have. You put a certain amount of energy in, and then you take a certain amount of energy to release the electron. Whatever is left is kinetic energy. There are a couple of questions. Does the metal affect the frequency threshold? And the answer is, of course. Potassium had its own one. As I mentioned, the examples in the Bunsen burner, barium ions, which behave very much like atoms for the photoelectric effect, potassium, sodium, all of them have very different ones. And that's why you can use the Bunsen burner test to identify what ion you have. Barium is always green, potassium is always pink, and so on. Okay, so again, nothing happens if you don't put enough energy. And even if you put in a flood of photons, if none of them are enough to kick the molecule into the upper state, you will get nothing off. Okay, so that's the second example historically that we wanted to look at. Okay, next let's look at the Compton effect. And again, I'm going to look at a prettier picture of it than I have above. And here is basically what happens. Now, realistically, this is a very great oversimplification of how you can do an experiment. We're pretending we have an electron sitting still and we're hitting it with a photon. In fact, in the real experiment, what you do is you have a multitude of electrons being hit by a multitude of photons, and then there is a statistical analysis done to see what kind of velocities the electrons have and at what angles they come off and things like that. But to understand it, we're still going to pretend it the way I show you. So we have a photon coming in. Here is a pretty little electron, the minus sign with a circle on it. The photon hits it, the electron goes off in this direction, the photon goes off in a different direction. As always, the electrons will have a kinetic energy 1/2 mv squared and a momentum mass times velocity. And here again, we will, as someone just asked, conservation of momentum and conservation of energy. Now, I've already told you that energy is h nu, Planck's constant times frequency. But here I'm going to contend that momentum is given by h over lambda. And this is called de Broglie's equation. If anyone in the class properly knows how to pronounce French, you can correct me on that. But here's a picture of Louis de Broglie, got the Nobel Prize for Physics in 1915. And he got it for writing his PhD thesis. So I've had a lot of students get their PhD theses in my research group. Typically, the thesis is 200 to 300 pages long, lots of pictures, experimental details, a lot of theory, and so on. Louis de Broglie's thesis was 15 pages, but it was so profound and important that they gave him the Nobel Prize for it. And as we'll see, it's been experimentally proven to be correct. And the Compton experiment was one of them that indeed showed the equation to actually work. So here he's tickled pink, and we'll see a picture of him later again. Okay, so let's go back to looking at this. So this again is the same picture I had before. And notice here is our conservation of energy. We start off with energy h nu for the photon only. And the final energy is going to be h nu final energy of the photon, which has to lose energy. So its frequency is going to go down. Its wavelength is going to go up. And then here we have the energy, kinetic energy that we have for the electron. So the energy in, again, has to equal the energy out. Now, where de Broglie comes in, and this is the equation that we just talked about. And if you look at your notes, whenever I put something in a rectangular box like this, that's to tell you this is really, really important. So 40 years from now, if you don't give a hoot about physical chemistry or quantum chemistry, this is one thing I hope you remember, that particles are going to have momentum. And as we see in this particular experiment, light also is going to have momentum. So out of today's lecture, I think that's the main thing that you'll want to remember. Both light and matter are going to have wave properties and particle properties. Okay, well, this is de Broglie's relationship. And probably right here is the summary of his 15-page PhD thesis of what he came up with. So we had energy of a photon was h nu. Einstein said energy of converting mass into energy was mc squared, that we've all seen. And all of you should have learned way back in physics, wavelength times frequency is equal to the speed of light. So we just rearrange these equations. You can see we can first write lambda is equal to c over nu. And from here, we can write nu, the frequency is mc squared over h. So we have it upside down here. Since nu was in the denominator, we cancel out the c's. mc, it looks like a momentum term. It's not really, but it was close enough to convince de Broglie, and he writes h equal h over p as the wavelength. Okay, well, here's the momentum conservation. If you look at that relationship carefully and look at the diagram, we wind up having the photon and electron going off in different x directions. And so they have to, well, they actually both wind up going in the positive x direction. But their total momentum then has to add up to what we had to begin with in the x direction. Initially, we had no momentum component in the y direction, but at the end, we have the photon going off in one direction and the mass going off in the other direction. And when you look at these expressions, they lead to this relationship right here, which we're not going to get into, but you can understand by knowing the difference in the wavelengths, what the angle is that you have in this diagram here, right? What theta is. And then the other angle phi you can calculate by making sure that the momentum in the y direction up and down here cancels out. Okay, I have a couple of more x's.
Is there any conditions for those angles? Do they have to reach, I don't know, like a determined number, or they are arbitrary all the time?
Okay, I mean, there are constraints on the angles in order to keep the momentum balanced out, but we don't need to go into that kind of detail right now. All I'm trying to do is to show you the validity of the Broglie relationship and how the Compton experiment demonstrated this experimentally. Somebody else asked if we should worry about Brownian motion. We're not going to worry about that at all. Just remember what I said in the beginning. The picture I showed you is a super oversimplification. We don't have just one electron sitting still. You have lots of electrons moving randomly in all kinds of directions. And so you have to do some very clever statistics and mathematics to figure out exactly what's going on. Okay, so that's enough for number 2. Here's just a reminder, and I'm sure all of you know this, but it's very important that you're familiar with this relationship. Frequency, this is the Greek letter nu, again, times wavelength is equal to the speed of light. People knew about the wave properties of light way back in the 1800s. A fellow named Maxwell came around, and they're called the Maxwellian Equations. And they're written as differentials. And anyway, the wave nature of light was well understood. From high school trigonometry, you learned, I mean, this is a sine function. If I go from 0 to 0 here, that would be one wavelength. Or in the figure that I've shown you, you can start from this point and go to that point. That's also one wavelength. And the frequency, of course, is how many waves you have per unit amount of time. So the abscissa here is time. The ordinate is the energy. This will be the amplitude of the light beam that we have. Just also as a reminder, Newton, among other things, all his other formulas, he also studied light. He learned that you could separate white light, such as what we get from sunlight, into the different colors with a prism. Nowadays, people typically use gratings, which have the same effect, but are much more efficient than prisms in carefully separating the frequencies of light. Okay, so we have a little bit of time left. Let's go to our next experiment. I've already told you the conclusion of this, that the de Broglie relationship we just saw works for relating wavelength of light to momentum. What the Davis and Dermer experiment is going to show, it shows that particles, such as electrons, also have wave properties. I think I have a picture of the Davis and Dermer experiment, but I may need to go. Let me exit screen. And share screen again. That didn't work. Okay. Here's a picture of the Davis and Dermer experiment. So we have a target and we have an electron gun. So here's some kind of voltage. You can see it's generating the electrons. It focuses the beam. You get an electron beam coming off, and then you get a diffracted beam coming off at different angles. So you see the angle P here. And so you have a movable detector. And what you can do is you can detect then at what angles you are getting these electrons, and you can also measure what their kinetic energy is, and so on. So this is the experimental detail, and I'll exit this again, and we'll go back to our class notes, hopefully more efficiently. Okay. And so this is my poor man's version of the same experiment. Nickel crystal lattice here, electron beams. Beams come off at different angles. And this is a lot like using the diffraction grating. Most of you are probably aware that many spectroscopic instruments use diffraction gratings. They may have as many as 1,500 grooves per millimeter, and then you can have light come off at the frequencies that you want. Infrared range, visible range, ultraviolet range, wherever you want. Okay, so the point is light is diffracted and you can separate it by angles that it comes off at. And for the electron beam, it turns out the de Broglie relationship works again. Notice now for electrons, you can measure the kinetic energy coming off, so you know the velocity of the electrons coming off, so you can calculate the momentum. And then you can look and relate the momentum to the wavelengths that that electron has. So I'm calling that an effective wavelength, and that's going to determine the angle that you come off with off the experiment. Again, we won't go into great detail on this, but basically the important conclusion from this experiment and the other one is that both light and matter have particle properties, and they both have wave properties. Now, we've also seen that energy of light will come in packets, and they will be called photons. So the Compton experiment also demonstrated that we could think about individual photons as providing energy. You couldn't combine them to get enough energy to overcome the threshold. Okay, now I haven't done this before, but I'm going to try to take a poll of the class. And I guess I'm not going to do it again. I thought I had it set up. Okay, I'll try to set the expression up next time. I had it set up for a different Zoom session, but it's not working here, so I'll have to do it again. Okay, so we're done with what I consider the four most important historical experiments to tell us quantum mechanics was needed and life was going to be different, and we needed non-Newtonian physics and chemistry to explain things. The last two experiments are, for our purposes, rather more difficult to understand, but I'll tell you about them historically. And especially for the next one, I want to tell you about this because I'm friends with the grandson of the fellow who got a Nobel Prize for explaining this on an early basis. The experiment is called Blackbody Radiation. And if you know physicists, they like to have everything be absolutely perfect and pure. And basically, they want to have a box with an infinitesimally small pinhole there. The total inside is painted black, so you don't get any absorption of light. You heat this up, and then you look at the emission of light coming out, and you can see how much light you get off at different energies. In reality, almost any hot object, like a ceramic object, like your coffee cup, would work. If you just heat it up, it's going to emit radiation. It'll give off infrared light, which is low energy heat. It'll give off visible light. It'll give off ultraviolet light. And here are the wavelength ranges that some of these regions have. So here are the observations that people found. So this is kind of a funny unit to put, but that's what the book had that I took it out of. It's energy density per unit wavelength, but just think of this as total amount of energy coming off at a particular wavelength or a particular energy. Remember again, energy is inversely related to the wavelength. So energy increases to the left. When lambda goes to the right, we get lower energy. Okay, so if we heat our black box or perhaps your teacup up to 1250 degrees Kelvin, this is the curve that you have. You go up by 500 degrees, of course, you get more energy. And notice the maximum shifts to higher energy towards the left. You go up to 2000 degrees Kelvin, again, you're getting lots more energy, and lambda max increases. Okay, so initially this data was explained by the Wien displacement law. And as I said, I got to know his grandson. The Nobel laureate Wien got his Nobel Prize in 1911. His grandson, Carl Wien, was a physicist, or I assume now retired, at the Darmstadt Technische Hochschule, which is basically a technical university in Germany. So when the grandson was at A&M in the 1970s, we got to be good friends. In fact, when he left, I bought his VW Squareback from him. And at some point in our lives, we met in Darmstadt, and I visited him, and I was shown his grandfather's Nobel Prize. So it's a nice big hunk of gold, nowadays worth lots more than probably was even in those days. But anyway, I think that's the only actual Nobel Prize that I've seen in person. Well, to show you how things were in 1911 or before, all the grandfather did was he said, those curves we had up above, if we took the absolute temperature, multiplied it by lambda max, you get a constant which has this value. So basically, 2000 Kelvin times lambda max is equal to a constant. 1750 times that is equal to the same constant. And people were pretty amazed that there was some relationship to this. Well, a few years later, a fellow named Stefan comes along and he said, well, we can actually go further. We can take the energy density, and that's also going to be equal to a constant times the absolute temperature to the fourth power. So people were happy with that. They didn't give Stefan another Nobel Prize, but they thought they were making progress. But then experiments got better, and more experiments were done in the ultraviolet range, and people started calling this the ultraviolet catastrophe. So this is what the Stefan law would probably predict, this dotted line. And there was another law called the Rayleigh Gene Law, which also didn't work very well. Here's the formula for it. And what people found in experiments, actually the energy intensity decreased dramatically as you got to higher and higher energies. And there should be a textbook picture if you look in the book to go for it. Okay, well, turns out this is pretty complicated. We're not going to try to explain it. Max Planck came along, and I'll show you a picture of him next time. And so pretty much he managed to fix this. But the way that Max Planck fixed it was by saying we have to assume that light comes in energy packets, h nu, and we call them photons. So that's why we call this the Planck constant. In order to explain this law, Planck came along and said, whenever we have radiation of any type, infrared or visible or ultraviolet, we have to think of these as individual particles. You can't just think of this as bulk energy going to the system, going anywhere it wants. It's going to have to come in individual units. Oh, okay. Well, actually, I do have a picture of Max Planck here. I don't remember if I put this in your notes or not, but anyway, he's quite a famous German scientist. They have many national laboratories called the Max Planck Institutes. I spent a summer at one in Munich in 2009, I believe. And they're a lot like our national labs, like Los Alamos National Lab, Oak Ridge, Lawrence Livermore Laboratory in California, and so on. So Many people also consider him the father of quantum chemistry because he came up with an explanation for this particular formula. We have just 1 minute at a time, so let me tell you a little bit more about Max Planck. Again, you may or may not have this in your notes, but his Nobel Prize was in 1918 in recognition of this discovery of quanta. But like quite a few other scientists, I'll tell you about Ludwig Boltzmann later in the course, you may know about. Planck's personal life was clouded by tragedy. His 2 daughters died in childbirth. 1 son died in World War I, and another son was executed in World War II for his part in the assassination attempt on Hitler in 1944. So sometimes even scientists get involved in politics, and people are telling me this is in your notes, so I suggest read the whole thing, and so you have an idea of what the background comes from. Okay, I'll hang on for a minute or so, and then I need to sign up for my other class if anybody has any questions left. Again, feel free to email me if you have questions.
So will you say that wasn't because of Max Planck that the term quantized came to life?
When I'm saying quantized, whether I'm talking in energy levels or particles, it means it comes in units. It's sort of the difference between having integer numbers or analog numbers. If we have numbers that are integers 1, 2, 3, 4, 5, only those are allowed. But an analog number can be 1.34, 7, 6, or anything you want. So when we get to quantum mechanics, we're going to find only specific things are allowed for energy or for particles. So photons are going to have specific energies individually. You can't think of it as a bulk energy term.
Okay, thank you, thank you.
Sure.
This is very exciting. It's very interesting.
Okay, hope you keep enjoying. Okay, see you Monday. Have a good weekend, everybody.
Thanks.